Hello friends, subscribe my YouTube channel Altpedia information and press the bell icon to never miss any updates from us. The equivalence principle, explored by the succession of researchers including Galileo and Einstein, expresses the idea cellular limited that all objects fall in the same way, and that the effects of gravity India limited are indistinguishable from certain aspects of acceleration and deceleration. The simplest way to test the weak equivalence principle is to drop two objects of different masses or compositions in the vacuum and see whether they hit the ground at the same time. Such experiments demonstrate that all objects fall at the same rate when other forces such as air resistance and electromagnetic effects are negligible. More sophisticated tests use a torsion balance of the type invented by Albert Einstein. Satellite experiments, for example STEP, are planned for more accurate experiments in space. Formulations of the equivalence principle include the weak equivalence principle. The trajectory of a point mass in the gravitational field depends only on its initial position and velocity, and is independent of its composition. The Einsteinian equivalence principle, the outcome of any local non-gravitational experiment in a freely falling laboratory, is independent of the velocity of the laboratory and its location in space-time. The strong equivalence principle requiring both of the above. In general relativity, the effects of gravitation are ascribed to space-time curvature instead of a force. The starting point for general relativity is the equivalence principle, which equates free fall with inertial motion and describes free-falling inertial objects as being accelerated relative to non-inertial observers on the ground. In Newtonian physics, however, no such acceleration can occur unless at least one of the objects is being operated on by a force. Einstein proposed that space-time is curved by matter, and that free-falling objects are moving along locally straight paths in curved space-time. These straight paths are called geodesics. Like Newton's first law of motion, Einstein's theory states that if a force is applied on an object, it would deviate from a geodesic. For instance, we are no longer following geodesics while standing because the mechanical resistance of the earth exerts an upward force on us, and we are non-inertial on the ground as a result. This explains why moving along the geodesics in space-time is considered inertial. Einstein discovered the field equations of general relativity, which relate the presence of matter and the curvature of space-time and are named after him. The Einstein field equations are a set of 10 simultaneous, non-linear, differential equations. The solutions of the field equations are the components of the metric tensor of space-time. A metric tensor describes the geometry of space-time. The geodesic paths for the space-time are calculated from the metric tensor.